This one equation stole the thunder from Sir Isaac Newton. Let's talk about the Euler-Lagrange equation. So in Newtonian mechanics, everything is defined in terms of position and momentum. You're interested in a particle. Where is that particle? That's its position x. And then how fast is it going? That's its momentum or velocity, v. And we can ask what forces are acting on the particle. So if we keep track of the forces, then we can kind of crank the machine of Newton's second law, and we can write down the net force is equal to mass times the acceleration. And then you can just try to solve this equation to figure out what happens to this particle over time. This is vanilla Newtonian dynamics. But what happens if I kind of scrap this picture and instead I start talking about energy, and I talk about not position and momentum, but any generalized coordinates that can capture the system. So Lagrange defines this quantity L, which is defined as the kinetic energy minus the potential energy. Now, why is it this? There's a long story as to why the Lagrangian is defined this way, but nevertheless, it's going to be roughly the kinetic energy minus the potential energy. Now, this is not enough to generate the dynamics to have a fully fledged theory. What you need is some sort of principle that tells you how to take the Lagrangian and generate from it the dynamics. This is where Hamilton's principle comes in. First, you define something known as the action. And the action is basically taking the Lagrangian at every moment in time as the particle moves from point A to point B, and you just have to add up the quantity of the Lagrangian along that path. So we can take this from t initial to t final. This is called the action S. And still, this does not generate any dynamics. What you need is some principle from which you can have some dynamics, some future evolving state. So what we do is we say that the variation of the action has to be zero. In other words, this is called the principle of stationary action. So this principle of stationary action is enough to generate the dynamics. What we're going to do is actually solve this equation. This is an equation in the calculus of variations, and the result is going to be some differential equation. Now, we won't do it over here, but the result of this is actually the Euler-Lagrange equation. So what we get is that the partial derivative of the Lagrangian with respect to the coordinates, so in this case, we'll call the generalized coordinates q, that has to equal the time rate of change, the full time rate of change of the partial of your Lagrangian with respect to your velocities, your generalized velocities, which I will call q dot. And so this is known as the Euler-Lagrange equation. And in certain special cases, many cases actually, this recovers Newton's second law. What it says is the partial of the Lagrangian with respect to the generalized coordinate is equal to the full time derivative of the partial of the Lagrangian with respect to the velocity, the generalized velocity.